Welcome to the session on Maxwell's equations. Basically, there are two forms of Maxwell's equations, integral form and differential form. Totally, there are four Maxwell's equations which can be expressed in two different forms. So, essentially, in this topic, we have 8 equations. In terms of integral 4, in terms of differential 4. We shall be also discussing the word statements, the equations which are mathematically postulated, their word statements. So, total we have 8 statements, 8 equations, 8 statements. So, let us start with the Maxwell's equations in differential form. So, by default, whatever you are seeing here, 4 equations, they are referred as the Maxwell's equations in differential form, because you have del cross, del dot. This del cross and del dot involves dou by dou x, dou by dou y and dou by dou z. You cannot perform curl operation and divergence operation without using these derivatives. The differentials, partial differentials, partial space derivatives, x, y, z refers to the space coordinates. So, we say partial derivatives with respect to space. Now, coming to the first one, the first Maxwell equation is based on Faraday's law, and the second equation is based on Ampere's law. The third and fourth equations are based on Gauss laws. This is Gauss law for electric domain, this is Gauss law for magnetic domain. We kept the heading as Maxwell's equations, but not a single equation has been postulated by Maxwell. Faraday, Ampere and Gauss, these three physicists have made experiments and postulated their own laws, which are Faraday's law, Ampere's and Gauss law. Maxwell is a person who tried to establish a link among these laws, and he was successful. That's why we are discussing today Maxwell's equations. And what are Maxwell's equations? The set of 4 equations which form the backbone for modern wireless communication. There is no wireless communications without electromagnetic theory, and there is no electromagnetic theory without Maxwell's equations. They form the backbone. What Maxwell's equation says? Maxwell's equations says that it is possible to transmit information wirelessly, because these three scientists, Faraday, Ampere and Gauss, they carried out their work independently. Maxwell tried to establish interdependency among these laws. They did not bother about establishing relation with other laws, but he bothered, Maxwell, and finally he got these equations. These equations, they date back to almost hundreds of years back, in 1880s, when this paper was published by Maxwell. These 4 equations were published. It says that you can transmit information wirelessly without using wires. It was a very revolutionary thought in those days, in 1880s, and his Maxwell's equations were published in research journal, and that journal was read by many scholars across the world. One professor by the name Helmholtz, he was a professor, he got very much impressed by these equations, which says that you can transmit information wirelessly, and he insisted his student, Hertz, the same Hertz, unit of frequency, Helmholtz Professor Helmholtz asked his student Hertz to look after this paper. One Mr. Maxwell says that with his equations, he says that you can transmit information wirelessly. In principle, it is possible, he is saying. In practice, why don't you implement this? Why don't you perform research on that? So, he tried very hard. In the first instant, he was unsuccessful, but the second time, he was successful, Hertz. So, Hertz for the first time demonstrated the possibility of wireless information transfer. That is the reason in antennas, the basic antenna, the primitive antenna or the elemental antenna is referred as Hertzian dipole. As a honor for this person, Hertz, we say Hertzian dipole antenna, the basic antenna, elemental antenna. Why? Because Hertz is the person who devised the first antenna, the basic antenna. Why Hertz designed? Hertz practically demonstrated wireless communications. There is no wireless communications without antennas. In the block diagram, if you have an antenna, that means it is wireless communications. If it is wireless communication, you should have an antenna. So first equation of Maxwell is based on Faraday's law. What it says? The curl of electric field vector is equal to dou by dou t means rate of change, minus dou by dou t means the change can be increase or decrease. Here minus means decrease. Rate of decrease in magnetic flux density vector. This is the word statement for the Maxwell's first equation. I repeat once again. Maxwell's first equation is based on Faraday's law. This is referred as the curl of electric field vector is equal to rate of decrease in the magnetic flux density vector. Second equation. This is based on Ampere's law. The curl of magnetic field vector is equal to the sum of conduction and displacement current densities. Next, third equation, Maxwell's third equation, which is based on Gauss law. What it says? The divergence of electric flux density vector is equal to the electric charge density scalar. Next, fourth equation. This is also based on Gauss law. The divergence of magnetic flux density vector does not exist. 0 means does not exist. If you observe carefully, electric lines of force can diverge like this. If you have a positive charge, the electric lines of force will diverge in all the directions. Where it goes? Up to infinity. If you have a negative charge here, it will terminate here. If you don't know where the negative charge is there, it goes up to infinity. So there is divergence of electric flux density. How much divergence? Depending on the charge that is occupying this volume, that is charge density. Then why del dot B over is 0 here? Similar to electric lines of force, magnetic lines of force does not diverge. See, if you have a magnet here, north pole, south pole, line of force starting at north pole will end at south pole, and inside the magnet it goes from south to north. If you have a line of force starting at north pole, it goes up to south pole. Inside the magnet it goes from south to north. So the magnetic lines of force are spiraling there itself, north to south, south to north. So the lines of force are not diverging in all the directions, similar to electric lines of force. Hence we say in magnetostatics, here divergence of magnetic flux density does not exist. There is no divergence of magnetic lines of force, so it is 0. Now let us move on to the Maxwell's equations in integral form. Whether you write in differential form or integral form, there are 4 Maxwell's equations based on 4 quantities. What are they? Electric field, magnetic field, electric flux density, magnetic flux density. Here also if you take electric field, electric flux density, magnetic flux density, 2 curl operations and 2 divergence operations. Now here, what is this integral? We have here dl. That means it is line integral. dl, it is line integral. What is this? Closed line integral. Closed line integral. And what is here? Surface. Closed surface integral. If you take these integral forms and apply the appropriate theorems, you will get the differential form. Previous 4 equations. See, this is open line. If you close this line, what do you get? An open area. That means you can have a relationship between, geometrical relation between a closed line and an open surface. That's what you see here. This is open surface, this is closed line. Open surface, closed line. And what is the theorem? Stokes theorem connects line integral and surface integral. What it says? The closed line integral of any vector can be equivalently written as the surface integral of curl of that vector. That vector is E bar. It is surface integral ds. So you get in terms of del cross E bar. That's what you see here, del cross E bar. Similarly, second one also in the same manner. Now come here, closed surface. This is closed surface. This is closed surface. Inside the closed surface, what you have? Volume. That's why a closed surface is geometrically equivalent to volume. Now what is the theorem which connects a closed surface integral and a volume integral? Divergence theorem. Gauss divergence theorem, because you are using for Gauss law. Gauss divergence theorem. What Gauss divergence says? The closed surface integral of any vector can be equivalently written as the volume integral of divergence of that vector. That vector is d bar. Volume integral dv. So by modifying this, you get del dot in terms of del dot d bar. What do you have here? Del dot d bar. So by applying appropriate theorems on the integral forms, you are getting the differential forms of Maxwell's equations. Now let us go for the word statements of this Maxwell's equations in integral form. Integral E dot dl is nothing but EMF. In Faraday's law we have seen E is written as integral E bar dot dl. So what is the left hand side indicates? EMF. The EMF induced, the electromotive force induced around a closed path or around a closed conductor is equal to the negative surface integral of rate of change in magnetic flux density. There is a statement for this. Coming to the second one, if integral E dot dl is EMF, then integral H dot dl will be MMF, magnetomotive force. This is electromotive force, this is magnetomotive force. Here you have electric field, here you have magnetic field in the same format. So the magnetomotive force is equal to the surface integral of sum of the conduction and displacement current densities. This is a word statement for second Maxwell equation in integral form. Next, coming to third one, d bar dot ds. Integral d bar. D bar is flux density, electric flux density. If you integrate flux density, you get flux. If you integrate charge density, you get charge. If you integrate power spectral density, you get power. So by integrating electric flux density, you get electric flux. What is that equal to? Psi. Electric flux is psi. As per Gauss law, psi equal to Q. Now what does this represent? This represents Q. And how you can write Q? Charge is written as integral charge density. Charge is there in the volume, so Q is written as integral charge density. So what statement you can make from this? The integral of the electric flux density is equal to the electric charge. Fourth one, the surface integral of magnetic flux density over a closed surface, or you can say the integral of magnetic flux density over a closed surface does not exist, for the reason we have discussed earlier. The integral of magnetic flux density over a closed surface does not exist. So Maxwell's equations are 4 in number. They are based on Ampere's law, Faraday's law and Gauss law. That they can be written in two forms, integral form and differential form. They involve two operations, divergence operation, curl operation. They are written on 4 quantities, electric field, magnetic field, electric flux density, magnetic flux density. 2 fields, 2 flux densities, 2 each in electric and magnetic domain. So with this we come to an end of the discussion, Maxwell's equations.